Hey, all right, I want to talk to you today a little bit about special right triangles, okay? Special right triangles are right triangles that develop patterns, okay? We're finding the lengths of their sides and lengths of their hypotenuse. So there's two special right triangles that we really focus on here. We're going to focus on triangles that have 45, 45, 90 degree angles. And then the next video will focus on a triangle that has a 30, 60, 90 degree angle. So our 45, 45, 90 degree angle refers again, or triangle, refers to the angle measures in the triangle. Again, 45 degrees, a right angle, and another 45 degree angle. So what does that tell us about this triangle? One, it's isosceles, because we have two sides that are congruent. All right. Two, it also tells us that the legs are going to be the same length. That's the definition of isosceles. And here's the sneaky part, okay? We can have a shortcut. Instead of doing the Pythagorean theorem, if we had some numbers there, we have a shortcut. A pattern develops. If we did the Pythagorean theorem for every person in this class on a different 45, 45, 90 triangle, what we would find out is the hypotenuse would end up being whatever the length of the original leg is times the square root of 2. So a 45, 45, 90 triangle is, because of this pattern, instead of using the Pythagorean theorem, we can use, say, a shortcut that says the hypotenuse is equal to the length of the leg times the square root of 2 and simplify things a little bit faster, expedite things, be a little bit more efficient. So let's take a look at two examples, all right? Now, if I have this triangle here, I can see by the markings it's isosceles and it's a right triangle. So therefore, I can conclude that these two angles have to be 45 degrees. Okay. I can now do a couple things. I know it's isosceles, so my legs are congruent. So if one leg is 9, I know my other leg is 9 as well. Perfect. Now, to figure out the third side, we can use the Pythagorean theorem. We could do 9 squared plus 9 squared equals the hypotenuse squared. Square 9 and 9, simplify the radical, or take the square root of both sides, simplify the radical, and come up with the answer. Or we can use our rule that says our hypotenuse equals the length of the leg times the square root of 2. Check this out. Our hypotenuse, that's unknown. The length of a leg, that's 9. The square root of 2 is always there. Our variable is isolated, it is 9. 9 outside the radical, the square root of 2 inside, they cannot be combined, so this is our answer. The length of this leg is 9 times the square, or the length of the hypotenuse is 9 times the square root of 2. And we are going to be looking to keep these answers in simplest radical form. Another way to do it, we can use this picture down here that tells us our legs are the same. X generalizes things. It's saying whatever one leg is, the other leg is the same. And then to generalize it more, we use the same length, and multiply it by the square root of 2 to come up with our hypotenuse. So we can look at this and say, all right, well, if this is what x is, according to our map, according to our template, then this has to be the leg times the square root of 2. So there's a few ways you can go about doing it. Personally, I kind of like writing the rule down, but we can use this combination of things also. All right? Now, well, what happens if they give you the hypotenuse? Same thing. Okay? One, we can look and say, we have a rule that tells us our hypotenuse, doesn't matter what it is, if it's a 45, 45, 90 triangle, is equal to the length of one of the legs times the square root of 2. Okay. That's our equation. So let's identify and fill. Our hypotenuse is 8. Perfect. Our leg is unknown, times the square root of 2. So we can write our equation, and now we have to solve for it. x is multiplied by the square root of 2. So if I divide both sides by the square root of 2, I'm ending up with 8 over the square root of 2 equals x. But now I have to analyze it. You know, so you really, this is almost more like we're working with our skills, simplifying, using radicals to simplify than anything. So if we would multiply again, both the numerator and denominator by the square root of 2, because really that's just a version of 1, square root of 2 over square root of 2 is 1. So we're creating an equivalent fraction, 8 times the square root of 2 over 2. The beauty of this, right, when we multiply the square root of 2 by itself, that's really the square root of 4. Right? So a little sub-problem right there, that creates the square root of 4. And the square root of 4 is really just 2. And then the last thing we do is we look at our numbers outside the radical. Do we know what 8 divided by 2 is? We sure do. 8 divided by 2 is 4. So we can reduce, and our final answer is 4 radical 2. Okay. So again, I see a lot of students that get the setup okay. We're like, yeah, I can identify my hypotenuse. I can identify what the leg is. I understand I have to divide by the square root of 2 to get the length of the leg by itself. So it's the radical part that we have to kind of draw back on and think, how do we work with those again? Right? So, hope this helps. You get some questions on the radical piece, let me know. May the force be with you.